Okay, there's a midterm on Monday. 40 questions, multiple choice, everything until today. If I have given you something to read, you can expect to know that, and whatever you have to do in the book, you should know that. Okay? I'm not saying that necessarily will be in the midterm, but otherwise I wouldn't have given you to read if you. I mean, the midterm is just it's point collecting, you know. But actually, learning is a little bit more than point collecting, you know. But this is up to you. Anyhow, I'm not going to say anything more, otherwise I'm going to get mad, or you get mad. So we have the last time we talked about gases. We talked about the perfect gas or the ideal gas, so that each gas molecule or gas atom is independent of the other one. Okay? It doesn't have any forces in between. That's the ideal gas. We will also learn that there are forces in between. And with the simple gas law, we've seen this guy Boyle when he took a break from his suffocation experiments of small creatures that needed air to find out if air is important for breathing. That's about 400 years ago. He found out that the pressure times the volume is a constant. That means it's inversely proportional. Okay, you have pressure times the volume is a constant. The pressure is then a constant divided by the volume. So it's related proportional over 1 over v. So is the volume is 1 over p. Okay, that means when you have more pressure, the volume gets smaller. Okay, if you have a small volume, you have what? High pressure, exactly, good. And so I've shown this to you with the lung model here, that what you have, we increase the volume of your chest cavity, then the air rushes into the lung, and when we breathe out, we decrease the volume, and the air rushes out, and so this is a pressure change. And we also had this then, what else did I do? I didn't explain. We had a marshmallow experiment, okay? We had these marshmallows, we evacuated this desiccator, and suddenly the marshmallows became bigger and bigger because there was no pressure against it, so we decreased the pressure, it increased the volume. And so this is Boyle's law, and this is by constant temperature, of course, and it's different at each temperature. But we could assume that it was constant temperature here, because the temperature doesn't change significantly here while I'm teaching. Maybe when you're thinking it gets a little warmer here, but nevertheless, we cannot consider this a significant temperature change. So you plot this way, P over V, then you get these kinds of curves, or you reformulate this, or rearrange this. You plot P against 1 over V, you put this over here, 1 over V, then the constant is the slope of this here, and since there is no intercept, it goes through 0, and with this we have seen that, that's what we have seen, that P times V is a constant, okay? Boyle's law. Then we also know from the very beginning, Avogadro's law, that the volume of a gas, of an ideal gas, is directly proportional to the number of atoms or molecules that you have, to the number of N, okay? And Charles's law, he lived about 130 years later, that was in the 19th century, was it 19th century? No, 18th century. This guy lived in the 70s, this guy lived in the 18th. There's no guy here, okay? This guy, Charles lived in the 18th century, and he was the one who first built his own flying balloon, and he filled the balloon with hydrogen and put a contraption on there, so he was the first balloon pilot. So V over T, we have seen V over T is proportional, okay? When you decrease V, the temperature must also decrease. Or when you decrease the temperature, the volume decreases. And with this, you get at a certain gas, a fixed gas, you get again a linear relationship, and this goes to 0. And with this, we have a thermometer. Because if the volume is 0, then the temperature would 0. But there is no 0, it would be 0. There is no 0 volume. It doesn't exist, and it's not a gas. If it doesn't have any volume, it's not a gas. Okay? And even if you have a negative volume, then you would have a negative temperature. If you go to extend this here, you go down here with your volume, then the temperature you would go over here. That would be your volume would be negative, and the temperature would be also negative. It would go up here. Okay? And so this doesn't exist, and this means this is a temperature scale also. You can measure the volume of gases, and you can extrapolate or infer the temperature, calculate the temperature from it. And this would be for another gas. And so V over T is a constant, or V is a constant times T, okay? V over T is a constant, you need to remember that. V over T is a constant, and how did I show that? I had this balloon, and what happened? I decreased the temperature by putting it in liquid nitrogen. What happened to the volume? It decreased, okay? So the volume decreased and the temperature decreased, so this because this is the same value for the same gas, and the gas was air. And with this we have a temperature scale, and the temperature scale is the Kelvin scale, which is the Celsius scale, that's what you use in the lab, plus 273.15. That means that the 0 point in Celsius is 273.15 Kelvin. And this is at standard pressure and atmosphere. Standard temperature and pressure is standard temperature is 273.15. That's what I just mentioned. 0 degrees Celsius and 1 atmosphere. This is what we're having here. Okay, that's when you talk about these kind of gases, for example. And when you use these three here, and I haven't shown that to you, when you combine these three here, you get P times V is N times R times T, and this is called the ideal gas law. And so P is the pressure, V is the volume, N is the number of particles or moles, R is a constant. Will be given to you. T is the temperature in Kelvin. Remember, in Kelvin. And so mixtures of gases act independently. They don't care if there's another gas in there. They exert a certain pressure, and they have a certain volume. They take all the volume and exert a certain pressure. And then you have a second gas in the same volume. It doesn't care about the other gas because gases are not very dense. You know, there's a lot of room. So they exert a certain pressure. The pressure would be the sum of both of the individual pressures. So the overall property is the sum of the individual properties. And this is especially for the partial pressure. So you can calculate the partial pressure for one component. You know how many of that component you have. You have the volume, you have the temperature, and you calculate the partial pressure of the second component. You have the volume and the temperature, and you also know what that gas is. That way you can calculate the number of atoms or gas molecules. So then we talked, and now we go back to the beginning after the midterm. We talked about many electron systems, so that the inner orbital electrons, they shield the nuclear charge from the outer orbital electrons. So there is this shielding of the electrons. They are in the way of the outer electrons, sort of, because you have the charge of the nucleus, and then you have electrons around, and the electrons are negative, the nucleus is positive. So the further out the electrons are, the less they see the charge of the nucleus. That means, of course, this has implications for ionization and so on and so on, okay? And we talk a little bit about this. So we have here a multi-electron atom, and this is how you build them up. So you have the 1s, and then the 2s, and the 2p, 3s, 3p, 4s, 4p. And the energy, when you build them up of the 2p here, they're not degenerate, okay? The energy of the 2p is higher, a little bit higher than the 2s. When you build them up, that's how you fill them up, okay? And so there is, of course, shielding. If you have an electron here, that's in the 1s orbital, it sees the nucleus without shielding, except if you have two electrons in there. They shield a little bit the nuclear charge, because it binds some of the nuclear charge. But if you have a 2s, this is filled here, and you have a 2s electrons in the orbital and the 2s orbital, so this is quite a bit shielded, because you have these electrons here, and so the nuclear charge sits here somewhere, and this time the nuclear charge sits here, actually, we go this way. Nuclear charge sits here, and so this doesn't see the nuclear charge as well, because it's shielded by this here, okay? And of course, as you go further out, the shielding is more and more. But you also have to consider that you increase the nuclear charge as you go along in the period, as you have more higher atomic numbers, okay? So, alrighty, where are we here? Yeah, and so this is it's the same. The 3d is higher when you fill it up. Okay, when you fill it up, the 3d is higher than the 4s. You see that here a little bit higher. All right. So the ionization energy I have is the energy that you need to exert on an atom to pull off an electron. Okay, and you can pull off more than one electron, and I will explain this to you in a minute. But when you pull off one electron, the ionization energy, remember, this is a positive number. Does that mean that we need to put energy in the system to pull off that electron, or does the electron go by itself away? Okay, that's why the number is positive. Remember, the level energy is negative, and it's 0 when it's totally separated from the electron is totally separated from the atom. It has nothing to do with that atom anymore. Then it's ionized. Then we say it's 0 or infinity actually. And so so you have a negative number, a large negative number, which is smaller and smaller for the levels here. But the ionization energy is the opposite energy that you need in order to pull it off that level. Is that clear? Sort of. Okay, good. So if we talked a lot about one electron systems, and the one electron system, you can calculate the ionization energy. Actually, you can sort of estimate the ionization energy. You know that one electron system has a charge here, and this would be, for example, hydrogen would be 1 over n, and this would be n equals 1, n equals 2, n equals 3, and so you can calculate the ionization energy from that. Now this would be here if you do that, for example. So we ionized here this electron, this first electron we ionized to the continuum. That means we removed it, we got it out the door, and that means the energy that you calculate here, if you go from, is 1312 kilojoules per mole. You don't need to know these numbers, but you remember that's a certain amount. If you use helium, and helium has now helium plus is a one electron system, but it has double the nuclear charge, and this is squared here. Okay, so that means that in order to go from helium, the ionization of that helium, the second electron, to take the second electron away from helium plus, you need 4 times as much energy than just for hydrogen as one electron. Okay, because the nuclear charge is hanging on much better to that. All right. So now, if we say helium itself, there must be some shielding effect, because you have 2 electrons in the 1s, and so one shields the nuclear charge to some extent. And if you go there, so the level, you can calculate the level here. That would be then you would have a many electron system. You would have to have an effective charge here, and the effective charge you measure ionization energies, and you know which level you come from, or you can determine this, and then you get these effective charges. All right, it's not that you have to know how they are. But so what you have here, you see that effective charge. You have 2 protons in the nucleus and 2 electrons. So if it would be fully seeing that if there would be no shielding, you would use, you would have to use twice that energy, okay? Because then you have twice an electron and you have 2 protons, you would have to double that energy. But it's not the case. It's not 26,024, it's 2,624. It is 2,372, so it's a little bit less. And you know why this is less? Because it's shielded, all right? So you need less energy to remove that electron here if you're in the if you have a helium atom. That's the helium effect, okay? Now if we do the following, we say, we have helium. Now we have a 1s, we have 1 electron in the 1s and 1 in the 2p, right there, okay? In the 2p. So now this electron shields that electron, is that right? All right, so let's look at the energy what we would have to use in order to ionize that helium, which is an excited helium, okay? So ionize the outermost one. This would be just the same. It's 328 kilojoules, not that much. There's a large shielding effect. And this would be the same like the hydrogen. Actually, this one electron here shields perfectly, essentially, shields that other electron. You see that? It's just like hydrogen here, all right? So we have then talked about the Pauli exclusion principles. You know that there are no, these are the 4 quantum numbers, N, L, M sub L, M sub S. We had a question about this the last time, so you should know that by now. I don't even know if there's a question or not, but about this. But anyhow, you should know that. So the Pauli principle is that you have, when you have no 2 electrons in an atom can have the same 4 quantum numbers. So this would be, would it have the same 4 quantum numbers? No, it wouldn't have the 4 quantum numbers. But it's also said wrong. So what is that? That's said wrongly here. So this would be also, because this is upspin and this is downspin. So this would be the perfect setting. Okay, this is the lowest energy situation. Of course, you can get to an energy situation like this by putting energy into the electronic system. Remember, I had an example. What was that example? Where the spin flips. Was oxygen. Remember, the spin flips and it absorbs light, and the spin flips goes back up. Spin flips, that was oxygen. So this is no good here. So this is Hund's rule. Let's see. So parallel spins first in the lowest orbitals. Okay, so that means this and this is not good. All right. So that everybody knows that, I think. What are you laughing? Is that right? I've been talking about this forever, okay? So we talked about electronic configurations and the build-up principle, the Aufbau principle. No, what? And the Aufbau principle. So you fill in your 1s, then you fill in the second one in the 1s. Okay, you can say if it's paired, then it's not magnetic. If it's unpaired, it's magnetic. And then you come to the next period. If I'm lazy, I write here helium. I take this 1s2 away and write helium, because this is the core here. It will not change. And so now I have lithium as that core here, helium 2s1, for example. And then they have helium 2s2, okay? Now you come to the p orbital for boron. This is helium here, 2s2, 2p1, and so on, and so on, and so on, okay? And okay, then we talked about orbital blocks in the periodic system. So the period goes from left to the right, means that you come to the next higher principal quantum number. And then you have here blocks here. This is the S block, 1s1, 1s2. That's the only one which has an exception here. This is 2s1, so 1s2, 2s1, 2s2. 2s2, 2p1, 2p2, 2p3, 2p4, 2p5, 2p6, okay? So this is the p block here. This is the s block, and in between you fill the d's here. Then when you get to 4 and 5, you start filling the d's, and you also start filling the f's here, okay? When you are here at the 6th and the 7th level, you're filling the f's here. You know that these are alkaline metals, and these are alkaline earth metals. These are the halogens, for example. We call them the halogens here. And these are the, what else did we call them? Inert gases, yeah? Noble gases. They're not that noble, actually. They like to partner if you give them the right partner, okay? So we showed you some examples. Well, I showed you some examples. And so homologues, you know what homologues are? Yeah? Homologues are elements that have in the same group. A group is this here. This is the alkali metal group. That's the alkaline earth metal group. That's the halogen group, okay? This is the halogen group, okay? Fluorine, chlorine, bromine, iodine, acetylene, okay? That's the halogen group. And so what have they in common? The same valence electron configuration, just in the next higher principal quantum number. So this is a 1s1, 2s1, 3s1, 4s1, 5s1, 6s1, 7s1, and this is a 1s2, that's not a homologue really, 2s2, 3s2, 4s2, 5s2, 6s2, 7s2, okay? So why do we call them homologues? One of the answers is, of course, that we have the same outermost electron configuration. We call this the valence electrons. But why do we sort of rely on these homologues? because they behave chemically similar, because the bonding happens with the outermost electrons, and there is some similarity in the compounds that they form. So for example, compounds of potassium, of sodium and potassium, sodium chloride and potassium chloride, there are similarities chemically, okay? And that's why we call them homologues. I can't go into further detail about this. So then we talked about ionization energy. Ionization energy, let's go first to electronegativity. Where is it? Okay, electronegativity. Electronegativity is an arbitrary number. This was studied by Melvin Calvin, and he studied hundreds of compounds, and he see that within compounds, some when there are several atoms or two atoms in general, one atom sometimes likes to pull the electron much more to itself than the other one. So one gives part of the electronic density and the other one takes it. So that the highest electronegative atom or element is what? Fluorine. Okay, and the lowest one? Francium. So the electronegativity increases from left to right and decreases from top to bottom. Okay? So if you have, for example, so it increases within a period and decreases within a group. That's what it says right there. Okay? Now, when you have the atomic radius itself, increases, you have within a group, the atomic radius increases. That makes sense. Because you go to the next, you have all these electrons of the one principal quantum number, then you go to the next principal quantum number, you have even more electrons, and then you go next principal, you have more electrons, okay? And with this, if you go that the atomic radius increases within a group, because you get all these electrons in between there, right? If I point at the periodic table, let's do this. Let's not be confused with this here. So that increases the atomic radius. Let's see, I have a picture probably here. Yeah, exactly. So that increases with the atomic radius increases, but then when you go from the left to the right, that means within the period, it decreases. Why is that? Because you have more nuclear charge, and it pulls the electrons closer, even if they're shielding, but it pulls it closer. So which one would be easier to ionize, this one or that one? Lithium. Why? Because this one pulls the electrons much stronger than this one, okay? So what this one would, these guys would ionize easier, and these guys would do what? They would pull electron affinity. They take up an electron. They would not like they try to pull that electron away from somebody, from atoms on this side here, okay? So when they do that, you have ionization, okay? Now there we have to go back to ionization. When you have ionization means, ionization, we talked about this at the very beginning of this lecture. So is this in green? What does that mean? That's energy that ionization energy, you have to put in, isn't that right? Yeah? I don't know if I have the colors right. Ionization energy, if you ionize something, do you have to use energy or not? Okay, so ionization energy is positive, okay? So the sodium, you need more energy than for the rubidium, because sodium is here, rubidium is there. So it became larger, that atom, and with this, the pull of the center, the pull of your nucleus, the nuclear charge is not that strong anymore to the outermost orbital, and so this is of course removed easier if you go from sodium to rubidium. Rubidium can ionize easier than sodium, okay? And so if you look at this side here where you have high electronegativity, so chlorine, bromine, and iodine. Chlorine, so when it takes an electron on, does it do what? It releases energy, or does it, do you need energy to have an electron put on an electronegative, as the name says, on an electronegative atom? We get released energy. That's why there's a negative number. It's electron affinity. I'm pointing at the wrong thing here. It's electron affinity. So this has the highest electron affinity. It releases the most energy. And if I talk about bromine and iodine, so how would that? So this likes to the most. It really likes to pull electrons in. Okay. Why is this? Doesn't this pull as easily electrons in than this one? Not as electronegative, and also the same thing is again, it's the electronegative, but it's also a function of the nuclear charge, of course. Now you have more shielding around it, and so the nuclear charge is not that effective. You can also look at it this way. And the same that even is less likely for iodine because you're down here already. Okay. So this is important that you understand these connections, these interconnections, okay? Now we see that the ionization energy, and this is what it actually shows, the ionization energy, the first ionization energy goes from hydrogen to helium, the other nuclear charge wins, okay? And then you come down, you have the shielding effect, and this is low, the ionization, and then as the nuclear charge increases, it goes up again. And next period it goes down and then up again, down and up again, but now it's not as pronounced anymore because you have all these electrons around there, and so they are much easier to ionize, okay? So the first electron to ionize is pretty easy of some compound, but if you have the same nuclear charge, but less electrons when you rip one off. So the nuclear charge is the same, but you have one less electron, so it can exert a stronger force on these. It binds them stronger than when you would have that extra electron on there, or not that electron. So when you have the second one you want to remove, that will be more difficult, won't it? Because now the nucleus hangs on even stronger to the electrons because the nuclear charge didn't change. And so when you want to remove the fourth one, it takes a tremendous amount of energy. You see that it takes about 20 times as much energy to remove the fourth one, this is in kilojoules per mole, than the first one, okay? So that's also one of these interconnections that you need to understand. We had talked about this, and we talked about this. Then when you have bonding, there are three different kinds of bonding, and we have explained this with electronegativity. I better step on it here. You have electronegativity is if you have you are here with a relatively electropositive or less electronegative atom, so that tries to become an ion, okay? Gets ionized. And this one here tries to attract an electron, okay? So if you have now the difference between sodium, that's the electronegativity, sodium and chloride. The difference is 3.2